Hello future engineers, welcome to my YouTube channel. If you're still new to my channel and you like what I'm doing, please don't forget to share my videos to your friends and to your friends' friends. Also, if you find my videos interesting and important to your studies, please don't forget to subscribe. Uh, that's the one way. That's one way you can help me promote my channel to keep me going, inspired and refreshed. Problem 38. The cross-section of a concrete dam is as shown. For a 1 meter wide dam section, determine the factors of safety against sliding, overturning, and the resulting soil pressure. Neglect Part A, neglecting hydrostatic uplift, and letter B, considering hydrostatic uplift that varies from 75% of the full static head at the heel to 0 at the toe. The unit weight of concrete is 23.6 kilonewtons per cubic meter, and that of and the coefficient of friction between the base of the dam and the foundation soil is 0.5. So here is the given cross-section of the dam. For the horizontal component, we have F directed to the left, and the distance from the bottom is 1/3 of 18, so 6 meters. Then we have weight 1, the distance from this vertical end is 2 meters, 1/3 of 6, so since B is 21 minus 2, so 19 meters from the toe, from A. Then this one, concrete masonry, call this W2. And since this is 1/3 of 6, or 2 plus 6, 8 plus 9, 17. So therefore, its distance from A is 17 meters as shown. Then weight 3 for this rectangular section of concrete. And the distance from this vertical is half of 6, 3 plus 9, so 12 meters shown. Then finally, for this triangular masonry, weight sub 4, the distance is 2/3 of 9, so 6 meters from A. Then we have the toe here, and this is the heel. F1 is, or F is equal to specific weight of water, half of 18 over 2 times 1 times 18. So F is equal to 1589.22 kilonewtons. Weight 1 is equal to 23.6 times 1/2 of 6 times 18 times 1. So weight sub 1 is equal to 529.74 kilonewtons. Then weight sub 2, weight 1 is water, so 9.81. 1/2 of 6 times 18 times 1, so 529.74. Weight sub 2 is masonry, concrete, so 23.6 times quantity 1/2 of 6 times 18 times 1, that's the volume per meter. So weight sub 2 is 1274.4 kilonewtons. Weight sub 3 is equal to 23.6 kilonewtons times 6 times 18 times 1. So weight sub 3 is equal to 2548.8 kilonewtons. Then weight sub 4, masonry, 23.6 times 1/2 of 9 times 15 times 1. So it is equal to 1593 kilonewtons. So Rx is equal to F, and Ry is the sum of the weights. And the distance of Ry from the toe is denoted by bar X. So Rx is equal to F, 1589.22 kilonewtons. Ry is the sum of the weights, so it is equal to 529.74 plus 1274.4 plus 2548.8 plus 1593. So R sub y is equal to 5945.94 kilonewtons. Then the factor of safety against sliding is mu Ry over Rx. So factor of safety against sliding is mu sub s 0.5 times Ry 5945.94 over Rx 1589.22. So factor of safety against sliding is equal to 1.871. Then the righting moment is equal to weight 1 times 19, 529.74, weight 1 times 19, plus weight 2, 1274.4 times 17, plus weight sub 3, which is 2548.8 times 12, plus weight sub 4, 5093 times 6. So righting moment is equal to 71873.46 kilonewton meter. Overturning moment is due to F alone, so it is 1589.22 times 6, 9535.32 kilonewton meter. From here, we can now compute factor of safety against overturning, which is righting moment over overturning moment. So 71873.46 divided by 9535.32. Factor of safety against overturning is equal to 7.538. Next, let's solve for barred X, which is righting moment minus overturning moment over Ry. So quantity 71873.46 minus 9535.32 over Ry 5945.94. So barred X is equal to 10.484 meters. This barred X is greater than B over 3, which is B is 21 over 3, 7, and it is less than barred X, and barred X is less, which is equal to 10.484, and barred X less than B over 2, which is 10.5 meters or 21 over 2. So that means this is good design, and Ry is just closer to the toe by a little bit, but it's almost at the midpoint of the base. Therefore, though the soil pressure expected at the toe is a little higher than that at the heel, they are almost equal. So let's compute. Q is equal to, so E is equal to 10.5 minus 10.484. So E is 0.016 meter. Q is Ry over B, quantity 1 plus minus 6E over B. Because Ry is closer to the toe by a little bit, so we use plus in this calculation, and we use minus for the Q at the heel, or for the soil pressure at the heel. So Q is 5945.94 over 21, quantity 1 plus minus 6 times 0.016 over 21. So again, use plus for Q sub toe, and the soil pressure at the heel, use minus in this operation. So Q sub toe is equal to 284.4 kilopascals, and the soil pressure at the heel, Q sub H, is equal to 281.8 kilopascals. So they are expected to be close. So this time, considering uplift, which varies linearly from 75% of the full hydrostatic pressure at the heel to 0 at the toe. So that's the base. So 0.75 of 9.81 times 18 is equal to 132.435 kilopascals. So the uplift force, therefore, is the volume of this uplift pressure diagram. So the uplift force, and this is 2/3 of 21, so 14. Uplift force is 14 meters from the toe. So it is 1/2 of 21 times 132.435 times 1 perpendicular to the board or screen. The uplift force is 3090.568 kilonewton meter. This uplift reduces the value of Ry, and it increases the overturning moment. Righting moment remains the same. So Ry prime, therefore, is equal to Ry previous 5945.94 minus the uplift force 3090.568. So Ry prime is equal to 455.372 kilonewtons. Then for overturning moment prime, by the way, our righting moment is the same, 71873.46 kilonewton meter. Overturning moment is previous overturning moment plus the moment of the uplift force, which is 3090.568 times moment arm 14. So overturning moment prime is equal to 29,000.272 kilonewton meter. So factor of safety against sliding prime is mu ry prime, mu sub s ry prime over rx. So substitute 0.5 times 4555.372 over 1589.22, the value of rx. So factor of safety against sliding is 1.433, and factor of safety against overturning prime is writing moment over overturning moment prime. So writing moment is 71873.46 kilonewton meter over overturning moment prime 29,272. So factor of safety against overturning prime can now be computed, and it is 2.478. Then for barred x prime, it is writing moment minus overturning moment prime over ry prime. So substitute barred x is equal to 71873.46 minus 29,000.272 over 4555.372. So barred x prime is equal to 9.412 meters, and that is still greater than b over 3, which is 7, and less than barred x, which is 9.412 meters, and barred x is less than b over 2, which is 10.5. So this is still good, and we solved for E, which is, by the way, the Ry is closer to the toe, so the pressure, soil pressure at the toe is still greater than that at the heel. So E is 10.5, A prime is 10.5, so this is the soil pressure distribution expected, QT prime, then QH prime here. Then we have the Ry prime, which location from the toe is barred x prime, which is 9.412 meters, and the distance between ry prime and the center line is E prime, which is 10.5 minus 9.412 meters, so it is 1.088 meters as shown in the figure. So Q prime is ry over b, ry prime over b, 1 plus minus 6 E prime over b. So plus for the soil pressure at the toe, minus at the heel. So Q prime is equal to 4555.372 over 21, quantity 1 plus minus 6 times 1.088 over 21. So again, plus for Q sub toe prime, and it is equal to 284.4 kilopascals, then minus for Q sub heel prime, and it is equal to 149.5 kilopascals. So that's it for this problem. Problem 39, a wood stave pipe 600 mm in diameter is carrying water under a head of 45 meters. It is bound by flat steel hoops 30 mm wide, spaced 100 mm apart on centers. If the allowable tensile stress, in the hoops is 75 megapascals, determine the thickness of the flat hoops in mm. So for the solution, let's have the figure as our guide in analyzing this problem. So we have here the wood stave pipes bounded by steel hoops, bound by steel hoops, and spaced 100 mm apart. So this is the water level exposed to atmosphere, and the head is 45 meters as shown. And let's consider tributary area S, and the diameter is D, lower half. Then we have the hoops, the tension in the hoop. This is S, diameter D, tension in the hoop is T, and the tension is equal to allowable stress, in this case, sigma sub T times area of hoop. And this rectangular projection is subjected to pressure, then the area is diameter times S. So F is equal to pressure times diameter times S. So summation forces vertical equals 0. 2T therefore is equal to PDS, where T is allowable tensile stress times area of hoop, and the right side remains PDS. And replacing area of hoop by width 30 mm wide times thickness, so let's just call it BT. So 2 times quantity tensile stress BT equals PDS. The Pressure at the center is equal to specific weight of water times head 45, and let's express that is in kilopascals. Then let's express that in megapascals by dividing 1000. So 0.44145 megapascals. Substitute into the formula 2 times 75 megapascals times 30 mm times thickness in mm also is equal to 0.44145 megapascals. So cancel. 30 is in mm, thickness is in mm, so that's why the diameter must be in mm, and the spacing must also be in mm. So that's consistent. Thickness therefore must be in mm. Using the calculator, thickness is 5.886 mm. Problem 40, determine the maximum depth of water in one side of a rectangular concrete dam, 6 meters wide, if there should be no spillage of water over the crest of the dam, and if the factor of safety against sliding must not be less than 1.2 and the factor of safety against overturning must not be less than 1.8. Unit weight of concrete masonry is 23.56 kilonewtons per cubic meter, and the coefficient of friction between the base of the dam and the foundation soil is 0.6. Neglect hydrostatic uplift. So that means that for maximum depth of water, it should be flush with the crest of the dam. Therefore, the depth of water is also the depth of the rectangular dam, or the height of the rectangular dam as shown. So this should be the figure. Then we have F, distance h over 3 from the bottom, 1/3 of h. Then we have weight of dam, which is its distance from the toe is 3 meters. So that's the toe and this is the heel. So therefore, that's Rx and that's Ry. And F is equal to specific weight of water, barred h over 2, area 1 by h, so 1 meter by h, the area. So it is 4.905 h square, where h is the unknown. Then the weight is equal to 23.56 times volume, 6 by h times 1. So weight is equal to 141.36 h. Then Rx is equal to F, 4.905 h square. Ry is just the weight, so it is equal to 141.36 h. Then factor of safety against sliding must be greater equal to 1.2, and writing moment is due to the weight times 3, so 141.36 h times 3, 424.08 h. Overturning moment on the other hand is F times h over 3, so 4.905 times 4.905 h squared times h over 3 is 1.635 h cubed. So factor of safety against sliding must be greater than 1.2. Factor of safety against sliding is coefficient of friction 0.6 times Ry, 141.36 h divided by Rx, 4.905 h squared. So must be greater than 1.2. So 0.6 times Ry, which is 141.36 h, over Rx, which is 4.905 h squared, must be greater equal to 1.2. Therefore, if we solve for h must be less than equal to 14.41 meters. That is based on the condition that the factor of safety must not be less than 1.2. Next, factor of safety against overturning, writing moment over overturning moment, must be greater than equal to 1.8. So substitute writing moment 424.08 h over 1.635 h cubed must be greater equal to 1.8. If we solve for h, cancel h here. So this is h squared. So 424.08 square root of quantity 424.08 over 1.635 times 1.8. So square root of that value, that's h. H should be less than equal to 12.00 meters. So for these two conditions here, then h should be less than equal to 12. So that's it. To satisfy these two inequalities here, this should be the answer. H should be less than equal to 12. Because if you use this, then the factor of safety against overturning would be greater than 1.8. So h is less than equal to 12.00 meters. So that's it for this series of problems.